Wood is one of the most important natural resources and one of the cornerstones of our society. It is therefore essential to understand its formation in the forest and its behavior as a material. And that is what we investigate at the Jugend Wood Lab. My name is Joris van Acker, and together with my colleague Jan van der Bulcke, we will give you a couple of examples of how we use X-ray computed tomography. For more than 15 years now, we have our X-ray glasses on to look at wood. In living trees, but also for looking at engineered wood products. Our research taps into different aspects of what we call the forest wood chain. Understanding this value chain is key in a sustainable use of the woody resource. It all starts with the living trees in the forest, where we study forest growth and structure with focus on the formation of wood within a year, the growth of trees over decades to centuries, the detailed anatomy of tree species in temperate as well as in tropical environments. Once harvested, the wood can be used for different purposes, and we focus on product innovation, investigating properties and structure of the wood, but also engineered wood products. Finally, the actual use of wood is also part of our research DNA. How long does wood last? What are the threats to wood in construction? And by extension, the use of other bio-based materials in buildings. For all these aspects, we do use X-ray computed tomography scanners at the UGCT core facility.
One of the questions we ask ourselves is the exact timing of wood formation. We all know that trees start growing somewhere in spring and end somewhere in autumn. Fine-tuning that somewhere is important to inform, for example, large-scale vegetation models. Conventional techniques do exist, but we are building a framework to come to an objective assessment of the biomass formed during the growing season using X-ray CT scanning. One takes a small piece of wood, puts it in the X-ray CT scanner, and we get an intricate look inside the 3D volume. The top example is the growth of an oak tree at 2 different times, where you can clearly spot the amazing development of these large black holes, which are actually the vessels the tree needs for transporting water from roots to canopy. The sample at the bottom is from a beech tree, showing again the development of wood, indicated by the yellow line that is ongoing during the season.
If we zoom out, then we no longer focus on the within-year development of wood, but try to understand how trees perform in function of climate forcings. Drought events, temperature changes, and decadal and centennial timescale. Trees do function as sensors of the environment, and the fact that they store this information in their tree rings makes tree ring analysis a very powerful tool. For this purpose, we do take increment cores. We put them in the scanner and can look at their rings and biomass in function of time. What you see here is the growth of beech from the Zonian forest in function of time, with a clear difference between living trees and trees that were uprooted by wind, showing that the uprooted trees were already heading for a fall for years. Another example is the enigmatic bristlecone pines trees that can grow thousands of years old. They can help us understand and reconstruct temperature of the past millennia by power of their rings.
Given that wood is a multi-level material, the study of its structure at high resolution is also key for the correct identification of wood, understanding its material behavior at macro scale, the impact of modifications on cell level, and many other applications. For that, we use even smaller samples and get an astonishing view on the internal structure. This is a 3D rendering of a softwood sample measuring not more than half by half a millimeter, scanned at submicron resolution, where you can see the detailed features of the wood. The principles of tree ring analysis and wood identification can be applied on wooden archaeological objects and art objects as well. And that is where the power of X-ray CT scanning really blossoms. Such precious objects cannot be sampled destructively. Thus, we need a non-destructive technique. This is an example of an ethnographical object from the Royal Museum for Central Africa that is scanned in full, but also zoomed in on a region to be able to perform wood identification. The other example shows a piece of archaeological wood wrapped in plastic foil, but thanks to the power of X-rays, we can look straight through it, do tree ring analysis, and date the wood.
But we don't only study solid wood. As mentioned before, we do also investigate the behavior of engineered wood products, such as wood-based panels. This is an eminent example of the use of X-ray CT scanning for dynamic imaging. What you see here is the layout of an experiment where a small piece of MDF is put in a miniature climate chamber in the scanner, during which relative humidity is changed, and we want to visualize the structural changes within this hygroscopic material. MDF, or medium density fiberboard, is an engineered wood product often used in furniture and flooring, but untreated it is prone to dimensional changes by moisture. With this approach, we thus can study the material at high resolution. Scans were taken with a resolution of approximately 2.5 micron and unravel the fiber-to-fiber interactions and stress levels in the material as seen in the colored cross-section.
Wood is also a biological material. As such, it is prone to attack by fungi if circumstances are favorable. Once again, X-ray CT scanning comes to the rescue for a better understanding of the mechanisms behind decay and decay patterns. In this particular experiment, we exposed small pieces of wood to fungi in a petri dish, of which a stack is scanned, indicated by the red arrow. This 3D rendering shows 3 wood blocks waiting to be consumed by the fungus. We do not only generate nice imagery, but are also able to quantify the mass loss in function of time, expressed as a change in local density. This helps us in understanding the impact of structure and chemistry in the wood-fungi interactions. With this, we are at the end of our presentation, and of course we do much more research with and without X-ray CT scanning than presented here. So if you want more information, send us an email. Do check out our website with an overview of all our staff members, projects and project collaborators. And of course, feel welcome to follow us on our social media. Thank you very much.